Okay, so yeah, I want to make sure it's a recording. Yeah, I guess so. Yeah. Okay, so this week we're gonna starting a new topic called inventory system or inventory models. So apparently this is something about inventories, because we can see inventories in everywhere for logistics, especially if you go to IKEA or IKEA. So you'll see a warehouse with a lot of inventories. So we are going to stay here for around 2 weeks, but most of the theories and formulas and calculations and models will be discussed in this week. And next week, we're gonna talking about a lot of questions about inventory models and how the calculation, how the questions will be asked in the final exam, and how we're gonna solving the problems by using some models. Okay, so the last 2 weeks, okay, let's get started. So we're gonna talking about several objectives, and first of all, why? Always starting from why do we need inventory system? Why do we need to manage the inventories? And what is inventory? And is there any way to classify different types of inventories? And why this is important? Maybe because of the cost. So actually this is a very, you will be surprised so how simple it is, the reason why we need to discuss inventories, only because of the cost. And so we're going to introduce economic order quantity model. So this is about how we're going to calculating the optimal, sort of optimal and inventory level and optimal inventory quantities. And we're starting from very basic configurations, assuming a lot of conditions. And then we're going to assuming some of the conditions are not there. We're going to relax some constraints and do a little bit more practical with two non-instantaneous receipt and shortage, just 2 cases. Okay, let's get started. So I guess probably if we're talking about inventories, and the first picture you might think about is if you're going to IKEA or IKEA, I don't know what pronunciation is correct, or sometimes people say IKEA or IKEA. So this is a warehouse. If you go to IKEA, so you will see a huge inventories stored there. So what is inventory and why do we need inventories? Apparently that's meet the customer demand immediately. So if you go to IKEA and buy something, you can immediately get what you want. So maybe you want to buy huge furnitures. That's fine. So we have a warehouse in here, so you can immediately deliver by yourself, or you can ask us, IKEA, to deliver for you. So we can immediately meeting the demand. And also, if we don't know the demand exactly, we probably do some forecasting, and so we can meet the anticipated demand. We assume maybe in the future we have a certain demand, so we do some forecasting and we store some temporarily store some products, and we can meet the requirements from the customer immediately. And also, if we are not certain, maybe we're gonna temporarily store something more and to keep the the products or the something intermediate process on our hands and try to make sure everything's fine. And also we can try to make sure we can meet the seasonal or cyclical demand. And so, from the viewpoint of the cost, because if you're ordering a large amount of products from basically your suppliers, so maybe you got some discount. Because that's the difference between a retail and wholesale. So that's also something we're gonna talking about. Okay, so what type of inventories? And we can see, sometimes we can see some raw materials inventories. That's to avoid delays for supplier problems. If you wanted to produce something in our production line, so you need a lot of basically raw materials. So not necessarily to be agriculture things. For example, if you're running automobile companies, you need thousands of, or maybe tens of thousands of different raw materials and from their suppliers. And maybe you have to keep something on your hands to make sure everything's fine to maintain your production lines. And also, if you have an operation or manufacturing line, and what you hope to do is you hope to make everything basically as smooth as possible. So what you want to do is for every step in your production line, you have maybe some inventories, and before that step, just trying to maintaining every steps are going smoothly. So one of the major purpose for inventory is to decoupling consequence steps. So if we don't have the inventory before every steps, so we're going to have to wait the output from the previous steps. So that's not good, but maybe okay, but not good. What if something happened in the whole process? So that's the reason why we need to study inventory systems. And why this is very important? So only one reason is the cost. So and the cost is huge. So maybe much more than your imaginations, around 10 to 40%, maybe for some special things, even higher than this cost. For example, the vegetables and fruits, because for those type of products, it's very easy to turning bad. So the inventory cost is really huge. And sometimes for a company, if you're calculating the asset value for a company, probably 50% of the asset is from inventories. And inventory is not very easy to convert it to cash, but still tied up your monies in your company. So this is pretty important. So how many inventories we need to store temporarily? If we temporarily store too few, so maybe not easy to satisfy our customer. If too many or the percentage is too high, maybe tied up with too many monies or too much of our cash on the inventories. This is also not good. So how to determine the level of the inventories? This is pretty crucial. And in the production line, if you have the manufacturing line, so the most important thing is we need to decoupling the processes. We don't have to wait from the output for the outputs from the previous steps. So this is why this is very important. And what types of inventories can we observe? So basically several different types. From very beginning, we should have raw materials. So we should have some inventory from raw materials from our suppliers. And if we have some raw materials, we're going to have a lot of processings, and including maybe 100 different steps. For every single steps, we need to have some inventories from the previous step. So that's to maintaining the working process and maintaining the smooth of the whole production line. And okay, so basically this is a pretty academic definition for what is inventories. So anything countable, and anything could be stored, and could be used in operations. So this is a definition for inventories. So this is not something virtue. That should be something you could have that on your hands. And so what is the crucial problem for inventory management? So we need to determine the correct quantity. So what is the best quantity? What is the best inventory levels? If too many, maybe not good, and tied up too much money. If too few, maybe cannot guarantee the whole process. And also, what is the correct time, and how to maintain the cost. So this is the crucial and central questions about inventory management. So we're gonna talking about those questions and try to figure out what is the best way. Okay, speaking of the so inventories, because we're talking about inventory cost. So usually, how to determine which types of inventory is the most important? So there's only one factor, is the cost. So, because I think this is a ABC classification, because we're going to talking about that slightly later. And the classification for the inventory, so it's only determined by the annual expenses. So the more money you spend for the certain inventories, the more important. So it's very important. So the crucial thing is how we're going to determine the money or the expenses for certain inventories. Yeah, maybe the value is important, but so additional to the value of the certain products, we might have some more cost on certain inventories. For example, the ordering cost. So for something, if we order for one time, so that cost for, we have a certain cost. But if we're ordering for 100 different times, maybe we have a quite different cost. And also the inventory itself, how to store, how to keep the in our company. So maybe cost takes a lot of time and monies and labor times. It's pretty important. So this is a pretty roughly classification. For some of the items, if the quantity is 15%, but yeah, it's 15%, but you know, speaking of the value is probably a big percent. So that could be 75 or even 80%. So that's going to be the most important and most crucial part of the inventories. But how to determine that? How to determine the value? So that's something we need to discuss for today. So now we think about, what if you are a manager for inventories in a supermarket? So what you need to do is figure out the cost for inventory. Maybe you think of inventories, that's pretty easy, just how much it is. Yes, that's just part of the inventories, but we have to consider additional to just the value of the certain products. So how many elements of the inventory cost? So basically we have three major types. And the first one we call that carrying cost. Sometimes it's also called holding cost. Basically this is the same meanings. So this is the cost of holding certain things in storage. Why do we have a carrying cost or a holding cost? That's pretty easy. The first, we need to have a place to temporarily store them. So warehouse. So we need to rent or buy some place to temporarily store. Or heating, maybe. Or refrigerating. That takes basically a lot of money. And lighting, maybe. And also security. We need to keep it safe. And we keep it recording, we need auditing. So this is all the costs relating to the carrying and holding cost. And also we have some indirect store cost. If you buy a lot of products there as your inventories, that tied up phones. If you buy a lot of inventories there and temporarily store for a year, and that's basically a lot of money because money has time value. If you have a £1,000 Titan there, that may be fine, but what about 100,000 or maybe 100 million? So that's going to be a huge amount of, because the money value. If you're tempering your money for a year, so even just including the interest rate, that's a lot of money. So this is indirect storage cost. So carrying cost or holding cost, that's basically the major important part of the inventory cost. So sometimes that could be vary, but for most of the cases, and we consider the carrying cost based on per unit and per time. So, and that could be calculated at a percentage of the inventory values. So in most of the cases, we consider it as 10% of the value of the certain products. That's the carrying cost, or maybe higher percentage of that. So, but anyway, we're gonna calculating most of the cases for carrying cost based on how many units we're going to store and for how long. And usually the times and units could be 1 year or 2 years. And this is the first type, carrying cost. And second type is ordering cost. So that's basically the cost that we order the certain inventories. Okay, so why do we have an ordering cost? That's pretty simple, because we need to ship. If we're ordering for something large, and for example, for rices and then agriculture, so that needs a pretty huge shipping cost, transportations, because we discussed that before. And also purchase negotiations. So every time if you buy just 1 ton of raw rice, maybe you have a certain price, But what if you buy 100 tons of a certain rice? Maybe the price going down a huge percentage. So wholesale price and retail price, that could be quite different. So maybe you think about, okay, that's fine. I want to order the more the better. So maybe, but the problem is that the more you ordered as your inventories, so the higher your inventory cost will be, because the higher the cost you temporarily store them will be. So how to determine that optimal level or optimal quantity of the ordering? That's something we need to think about. And so usually we're gonna thinking about or consider the ordering cost by how many times you want to make an order. So if you want to make, and we consider ordering cost as for example, a constant thing, constant cost, but we consider the total ordering cost by how many times you want to make order. And so why do we consider it like this? We're going to have an example to simply explaining the theories behind ordering cost. And so if you are working in a supermarket, and we call that ordering cost, but if you are working in a production line, so we have a very similar concept, but with a different name called setup cost. So what does it mean? For ordering cost, it's pretty simple. So I want to order something, and for example, for the supermarket, I want to order some fruits and temporarily store in our supermarket and sell to our customers. That's pretty simple. But for the production lines, so usually production line in the practical, in the factory production line will be running 24/7, 24 hours a day, 7 days a week. But for some cases, if your demand from the market is not huge, maybe you're gonna run in your production line for 2 days, and then you're gonna stop for 3 days, and then you rerun for 2 days, and then stop for 3 days. So that's probably the way we're gonna run a production line. So every time when you're starting up your manufacturing line, so you need some cost. You're heating up, and you opening the air conditioning, and you're waiting for the warming up, so that's a certain cost. And that's basically the same thing as the ordering cost. Every time when you want to starting up your manufacturing line, you have a certain cost. Every time when you want to ordering a certain quantity of inventories from your suppliers, you have to pay additional to the value of the product itself. So this ordering cost and setup cost, that's basically interchangeable for different scenarios. And the last one, shortage cost. So that means sometimes, for some reason, we are short of inventories, but we still have some demand from our customers. So definitely this is some loss, because we have immediately loss of sales, because some people want to buy, but we don't have. So okay, so this is a loss, a potential loss. And for some big factories, maybe we have penalties, because you promise your customer, yes, I want to deliver something, but at a minute, I'm short of inventories. So that's going to be a problem. You're going to have to pay for penalties. And if the customer is internal, for example, the production lines, and you are in charge of a certain step, and the next step, the people waiting there for your outputs, so we're going to causing some work delay for the whole production line. So this is the shortage cost. Definitely, sometimes this is a huge cost. So 3 different types of cost. So we're going to consider them one by one, see how we're going to have some theories or how we're going to determine. So what is the main problem for inventory system? So usually 3 questions. How much we need to order for every time? If you're working in a supermarket, and for example, for fruits, that's easy to understand. You cannot order fruits for a month sales. No, you couldn't do that, because the fruits are very easily turning bad. So probably you're gonna order from the suppliers for fruits every day, maybe every morning. So this is for fruits. But what about small furnitures? Some mirrors or some small tables in supermarket, you can buy this also. Probably you could order that for every half a year, because for small furnitures, that's not easy to turn bad. So that's pretty much different for different products and for different and characteristics for products, and how much you need to order and when to order. So we don't know. So maybe we need to order every 3 months or 4 months or every 6 months. We don't know. We're going to determine that based on how much we need to order. And which items are the most important. That's based on the cost of the inventories. Okay, so to solve a little bit theoretical solve those problems, find out the end results, we're going to introducing a model called economic order quantity model. So, and this is the crucial keywords is the quantity. So we need to determine based on certain conditions. So how much or how many units we need to order for every time when we hope to aggregate inventories. And the purpose to determine order quantities and minimizing the whole cost. Because we discussed a lot of the costs, ordering costs, the holding costs, and shortage costs. We hope to minimize those costs. At the same time, maintaining the demand from our customers. Okay, so we have certain assumptions, and every time we have assumptions, we cannot consider every possible condition from the real world. So we assume we know the demand from the market, and the demands will not be changed for every year, so that's constant. Usually this is not true, because we have certain events and the weather, and so that's always be changing every day, but we assume probably we can forecast the demand for every year, and for every year that's constant. And also we assume linear quantity cost relationships. So we're gonna explain this later on. And also we assume constant delivery time, but usually the delivery takes quite different times. But we assume, for example, our suppliers are Superman, they can deliver by no time, so this is one assumption, or they can deliver always be within 1 day or 2 days. This is also some assumptions, but we assume and deliver time is constant. So this is a pretty optimal assumptions. And also fixed ordering cost. So every time we order, so the cost is the same, but usually it doesn't, that's not true. But for simplicity, we just assume ordering cost for every time that's the same. Okay, so this is some assumptions and basic conditions. Now let's try to consider 2 business scenarios. And this is actually the only scenarios we're gonna consider in our questions. So the first one, small supermarket. And so your business model is very simple because it is a small supermarket at a countryside. And you only sell one specific type of rice. And you don't do any processing, manufacturing. No, you don't do that. You just buy from your supplier. And this is a wholesale supplier. So you could buy from your wholesale supplier by a slightly cheap price, and you sell them to your local customers by a slightly higher price, so you can make money. You can maintain the whole business. So this is very simple. So the problem is that, and if you want to buy from the wholesale suppliers, how many times you want to buy in a year? Probably 4 times, or probably you want to say, every year I just want to buy 1 time. And so that's a huge buy. But is it the best way? We don't know. So how many times, we're going to determine later on, but this is just a simple business scenario. We are buying from the supplier and selling to our local customer. And very simple, we don't do any processing. Okay, so the first one and the second one is, what if we are doing some production line? We don't consider the raw materials, we just consider production lines. We produce something and sell them to our customers. And this is another scenario. Basically, they are pretty much similar, but when we do some productions, so that means we can always open our production line we like, but so we hope to find an optimal way. So how many days we hope to opening our production line? Maybe 3 days and pause or stop production line for 2 days, maybe, or opening a production line for 4 days or for 5 days. So what is the best way? So we're gonna figure out. So every time when we open our production, so we hope to produce something and so produce at the same time we're selling to our customers. So basically the speed of our production should be faster than basically the demand from our customers. Otherwise, we won't have any inventories. So this is also the case for the supermarket. So the speed we buy from the suppliers should be faster than the demand from our customers. Otherwise, we won't have any inventories. So if I think about abstractly, so this is a pretty similar process. So the first one is we always need to aggregate some inventories, either from ordering from the suppliers or we're gonna running our production lines and produce the products by ourselves. So we aggregate inventories and we're gonna sell to the customers. So we're gonna supply the demand. So we sell them for some days and then we sell out all the inventories. So when we have nothing to sell, so we're gonna re-aggregate inventory again. Maybe we reorder from the supplier, or maybe we reopen the production line to running production line and to aggregate our inventories. So this is basically the same things, but we have two business scenarios in here. Okay, so at the first, we're gonna consider the first one. What if we are now working at a supermarket, very small one, and we hope to buy from our supplier and selling them to the local customer. Okay, so this is pretty simple things. So this is the time. So this is about inventory levels. So how you want to aggregate your inventories. So this is time, and this is the horizontal, and the vertical one is the inventory level. So think about now you are running a supermarket at time zero. At the very beginning, actually you don't have anything in your supermarket. You want to do some order. You order from your suppliers, but your supplier is actually Superman, and your supplier can deliver your order instantaneously. That means it takes no time. So immediately after your order, so you receive all your inventories, and by next second maybe. So this is not true. So deliver always takes some time, but what if we assume, so we can have our inventories immediately after we order. Okay, so this is an instantaneous delivery. So at time zero, we have nothing, and we place an order, we immediately have all the inventories. So we can aggregate inventory level immediately to Q. So this time, we order Q units of the inventories. So what is Q? So we're going to talk about that later on, but let's assuming, so this is just a single Q. Okay. When we have inventories, now we can sell them to the customers. So we're assuming every day the consuming speed, basically the demand from our customers, is the same. So for example, the first day we sell a unit of 10, for example, and the next day 10 again, and next day 10 again. So every day we sell out some products, so the inventory levels will be decreasing by the same speed. So decreasing after the first day, and second day, and after some days, apparently our inventory running to be zero. So, okay, when we're running out of any inventories, so we're gonna order again. So, and we also assume, if we don't have any inventories, we immediately place an order and we immediately receiving all the orders. And we can aggregate inventory level to Q again by no time. So this is again, we order again, so we have the same amount of inventory as before again. So the next time we order, the quantity of the order is also Q. So we're assuming every time we order the same quantity. So the first time is Q, and the second time is Q. It takes no time to aggregate inventories. And then after that, we sending out to our customers and every day until one day, basically, if the speed is the same. So the first time it takes T time, and the second time, and it's also T. So in here is 2T. One times reaching 2T, we are running out of the inventories. Basically, we have nothing in our supermarket. Let's assume if 2T is 1 year. Okay, so if this is 1 year, so that means here it is the half year. So in the whole year, we place 2 orders. And every order has the quantity of Q. and this time is a Q, and next time is a Q. So in total, in the whole year, so we ordered 2 times, and the total of the inventory we order is 2Q, because it's 2 times, every time we order Q. Okay, that's pretty simple. And so, because we ordered 2Q, and we sold out everything to the local customer, so we assume for the local customers, so the demand of the whole year is just a 2Q. So usually we're using capital D to represent the demand for a whole year. So the total demand of the whole year is just 2Q. Okay. So if we know D and Q, for example, apparently we can calculate how many times we placed the order. So that should be the total demand divided by the Q. Because if we don't know how many times we ordered, but we know the total demand and the Q, so that's the quantity every time we place an order. So we can find out, okay, we basically ordered 2 times. We have 2 orders in the whole year. And average inventory level is Q divided by 2. Is it easy to understand this? I guess so. Because if we only consider for the first time, we order Q. And okay, so at the very beginning, we have a quantity of Q. And then every time we have decreasing, the quantity of the inventory are decreasing until T. So before the second order, we have the quantity of 0. So basically, this is from time 0 to time T, we have Q to 0. So on average, if you think about this, so this is actually a small triangle. If you place that small triangle to here, so on average, we have Q divided by 2. So this is half of Q as the average inventory level for 0 to time, and 0 to T. And we can do this the same way from T to 2T. The average level is also Q divided by 2. So for 2 time period, the average level is the same. So for the whole year, so the average inventory level are Q divided by 2. So this is the average level. But every single time point, we have different level of inventories. But on average, we can say we have Q divided by 2. Okay, so this is a crucial quantity. We're going to using that later on. Okay, so this is from the very simple figure. This is something we can find out. Okay, now let's try to using those symbols and to think about the problem. The first one is, because we discussed, we have some carrying cost. And usually carrying cost is to calculate by how many units you want to keep and for how long. So and that's basically based on the average inventory levels. And because if you consider, for example, carrying cost per unit per year, is that we're going to using C with a small c subscript in here. C is carrying, so C is cost carrying in here. So it's CC. So okay, so this is for per unit and per year. So in the whole year, we know the average inventory is this. So basically, how to find out the total carrying cost? So this is the average inventory times the per unit cost. So we can basically the average inventory is, and we calculate for every day. So this is basically the inventories we have for the whole year. And so we're using the unit inventory cost for carrying cost and times the average inventory level. So basically that's the average annual carrying cost for the whole year. Okay, so if you think about annual carrying, yes, please.
I just don't understand why we times it.
C with this.
No, Q divided by 2. Why don't we times it? Why don't we times it? So like Q, 2Q times CC, because that would be the cost for the whole year. Why do we have to do it on average?
Because that's basically the carrying cost per unit. So that's the carrying cost. That means that's not the total one. That's basically on every single time. So how many you are keeping in your house. So this is basically based on the average one. Okay. So because for 2Q, so that's only considered the 2 time point. At one time point you have Q, at another time point you have Q. This is just 2 time point. But we're going to consider for the whole year. So on average, we basically having Q divided by 2. So this is not peak, but we're going to have to consider the whole year. Yeah. So this is the carrying cost. So if you consider this is the whole cost, that's equals to CC divided by 2. 2 is a constant, and times Q. So this is actually a function of Q. If CC is a constant and 2 is a constant, that's basically the annual carrying cost is a constant times Q. So that's basically, if you represent as a figure, so basically this is the figure. So we have a Q, and this is the annual and carrying cost. So the bigger the Q is, so the bigger the annual carrying cost is. So this is basically the relationship between carrying cost and the quantities. Okay, so that means maybe we shouldn't, for every time that we order the inventories, we shouldn't order the bigger, the better. So this is not the policy for the global optimization. Okay, so this is a relationship between the quantity and the annual carrying cost. So this is one type of a cost. And another one is ordering cost. So before we jump into the ordering cost, so we're going to consider very simple. This is a simplified example. So what if the annual demand is this, just 10,000 kilogram? Okay, so we have several options. So what if we ordering just once and 10,000? And probably this is the price we can have. And also this is a delivering cost we can have. So for every kilogram. And what if we split it to 2 times? And that means every time we order much less. Or every time we're going to ordering even less or less. So this is several different types of orders. So what if, so this is a pretty small order. What if every time we only order 500 kilograms? So that means maybe we have pretty expensive price because every time we buy pretty small volumes. And for this time, so this is a pretty huge pie. Maybe we have a pretty cheap. So this is just examples, not from the real cases. But we definitely can imagine. So the more you buy for once, so the lower the price you will get. So this is a wholesale price. And also for delivery, so the more you want to deliver, so the unit price will be lower. So, but if you only deliver a pretty small things, and so the unit deliver price will be higher. So if you consider the total cost and total unit cost and times the quantities and total cost, so you will find out. And so we're gonna represent this as Q versus the total cost by these numbers and these numbers. You will find out, so what is the relationship between the Q and the total ordering cost? That's basically a hyperbolic curve. So it's something like this. So roughly you can say the higher the Q is, the total ordering cost is. And the lower the Q is, the higher the ordering cost is. So basically this is roughly the relationship. So now we know the total cost, when here the total cost is the total ordering cost. The total ordering cost should be something times 1 divided by Q, because this is a hyperbolic curve. And so this is the relationship. So we hope to find out ordering cost constant times, and this is 1 divided by Q to representing the certain relationship. So that's the theories behind our formulas. Usually, we're gonna consider the ordering cost based on the number of orders per day. So the how to find out the number of orders? So that should be based on the constant demand. Because we assume we know the demand. Okay, what if D is a constant? If we know the constant demand, and if we know the order quantities, we can find out how many times we need to order. So because we've done this before in previous slides. So D divided by Q, and if we know the cost per order is CO, so the cost per order is a CO. So this is for 1 order. And this is the number of orders. So we times them together, that's the annual ordering cost. So this is the per unit, and this is the time, D divided by Q. So this is representing a hyperbolic relationship. If CO, the ordering cost for every order, is the constant, and D, usually we consider that's a constant, and we assume we know what is D. So this is basically a constant times 1 divided by Q. So this representing a hyperbolic relationship. So that means the higher the order quantity is, and the lower the total ordering cost is. But the smaller the quantity is, the higher the ordering cost is. So this is the relationship between this ordering cost and the quantity is. Quantity is every time the quantity, how big your order is. Okay, so two types of order. So what if we consider them together? So this is the holding cost. We know for holding cost, so the bigger the Q is, the higher your holding cost is. And this is your ordering cost. So we know the bigger the quantity is and the smaller your ordering cost is. Okay, so if you combine this figure and this figure together, that's the total cost. Total cost should be equal to holding cost plus ordering cost if we don't allow the shortage. Now we don't consider any shortage. So we don't have any shortage. And because every time when we running out of inventories, we can immediately order and immediately aggregating all the inventories. So this is the assumption. So this is a very simple case. Now we have a very special curve in here as the total cost. Apparently, if we hope to find out a Q and to minimizing the total inventory cost, how to find out? Because apparently this holding cost is increasing with the increase of the Q, and ordering cost is decreasing with the increasing of the Q. So we should somewhere find out a point in here. That's the minimal total cost. Because if we go beyond this cost, beyond this point, apparently the holding cost will keep increasing. So the total curve will be slowly increasing. But before this minimal point, and apparently, so the ordering cost is pretty high. So we will also have a pretty high total cost. So we should find out somewhere there's a point. So where the point is. So basically we have two ways to find out. So, and this is basically the formula for the total cost. So, and this is the ordering cost. We've done this before, and this is the carrying cost. Carrying cost is CC. This is just for every unit, and this is the average unit across the whole year. And this is the ordering cost for every order, and this is the demand for the whole year. And Q is the quantity for every order. So if you add them together, that's the total annual inventory cost. So, and looking at this figure, so apparently we have two ways to find out the minimal point. The first one is the intersection, so in here. So intersection, that's the optimal one, because after that, we will see, so the holding costs will be increasing a lot. So basically, the total cost will be also increasing. And before that, so also the ordering cost will be pretty huge. So this is going to be the intersection of the two curves. So this is one way we could find out the intersection of these two curves. Another way is we could probably find out the tangent line. So I assume you know what is tangent line. So that's the first touching point of this line and this curve. So tangent line of the total cost curve. So, and apparently for intersection, that's pretty simple. We can make, at the intersection point, the ordering cost equals to the holding cost, because they are intersection point. So they have the same cost at this level. For the tangent line, so that's slightly more difficult. So we're going to find out the first derivative of the total cost to Q and make it to 0. Because for the first derivative is basically the tangent line, but we're going to make it to 0. That means that's the horizontal line. Okay, so it's the intersection that's basically equals to the tangent line, touching point. Okay, and this is the final result. And how to find out? One way, the red one, is the intersection. Because at the intersection, basically the ordering cost equals to the carrying cost. So we make them the same. So, because this is pretty easy to find out what is Q. So we can basically cross times the two things. So 2 COD equals to Q squared CC, and we can easily find out what is Q. And also we can find out the first derivative, because this is the total cost. And we are trying to find out the total cost, the first derivative of total cost to Q, and make it to 0. So this requires a little bit more math. You can find out the first derivative. For this part, it's pretty simple. The Q is here, so the first derivative is just CC divided by 2. For this part, it's slightly more difficult, but it's also fine. COD, that's a constant. And for 1 divided by Q, that's equals to basically Q with a -2 and power. And we make it to 0. We can also find out the same expressions in here. That's basically the same, the final expression of the optimal quantity of the order. So that only determines by D, CO and CC. So what is D? The total demand in the whole year. If we know the total demand of the whole year, and we know what is ordering cost and what is carrying cost, so we can roughly determine what is the optimal point for every orders. So if we know the optimal quantity of every order, is it possible to find out how many times we need to make the order? Probably, because we know the whole year demand, D, and we know every time we need to order Q quantity or Q units. So if we use the whole demand divided by Q, that's basically how many times we need to make order. So we're going to do some calculation later on using this. Okay, so this is all the formulas, and let's do some very simple examples. So we've considered a supermarket. Now let's just try to do some calculations based on supermarket. So if a supermarket wants to order the pallets of a certain rice products, we're always using this, and to satisfy the customer demand. And D, when we have a capital D, that means this is the demand for the whole year, just 10,000 pallets. Okay, so, and you know what is the CC, that's carrying cost. You know what is the CO, that's ordering cost. You know the two costs in here. So how to find out optimal order quantity? So that's pretty simple. So we're going to using this equation, because 2 times D, D is just 10,000, and times CO, just 150, and times the carrying cost. So we got 2,000 pallets. So every time we need to order 2,000 pallets, and to minimizing the total cost of carrying cost and ordering cost. Okay, so if we have Q optimal as 2,000 pallets, so is it possible to calculate something more? Yes, it's possible. So what is the total annual inventory cost? Because we know what is Q. Apparently we can substituting Q, the optimal Q, into this equation. Because we know D, that's still the D, and CO, that's ordering cost. And now we know the Q. So we can substitute in here, we find out this is the total ordering cost, and also this is the total carrying cost. In total, that's the inventory cost for the whole year. And how many orders have to be made per year? As we know, every time we need, the optimal way is to order 2,000 pallets. So, but for the whole year, the demand is 10,000. So apparently we should order 5 times. That's the optimal one to minimizing our own cost. So if we're not using 2,000, maybe we're gonna having slightly more cost in here. Okay, when do we have to make order? So that's basically depends on how many orders we need to make. So 5 times, apparently. So if we're assuming, so we are working 350 working days, so we divide it by 5, so apparently we should, every 70 days we need to make an order. So that's based on the optimal ordering quantity, 2,000. Okay, so is that simple? So this is a summaries for the first one. This is a very simplified model about ordering cost and carrying cost. So total cost, we're just assuming we have two parts, and holding cost or carrying cost, ordering cost. And so what we're trying to do is minimizing the total cost. So we don't like that cost, so we're minimizing that. So assuming the demand is known and the lead time for receive is constant, basically the 0 time to receive our inventories. So how to find out optimal quantity? So that's basically intersection point. That's pretty simple. And the holding cost should be equals to the ordering cost. You may have some test. So if you think about here, so this is the equation to calculating the ordering cost and carrying cost. Are they the same? Oh yeah, that's the same because this is the numbers here. So the 750. So and 2000, that's the optimal quantity we find out. And we're substituting to the equation of the total and ordering cost and carrying cost. They should be the same. If they are not the same, that's going to be a problem. But if we're substituting to them, yeah, we find out they are the same actually. So 750 for the ordering cost and carrying cost. So because this is the theories, we're going to, based on this theories, we derive how we're going to find out the optimal quantity. And we're substituting to the theory itself. So apparently we got the same result. Okay, so that's some basic summaries about the first basic and EOQ, economic ordering quantity. So this is the optimal point. So easy way to find out is making the holding cost and ordering cost the same. And if we could find out the Q, the optimal ordering quantity, so that's pretty easy to substituting the Q into the holding cost and ordering cost and to find out the total cost for the whole year. Okay, so this is just a starting point. We're gonna do something more later on. So we're gonna have 5 minutes rest and then we're coming back for more topics. Okay. Huh? Sorry?
Are we going to be given a formula in exam?
I'll answer you later on. We should start again. Okay, so in the first hour we talked about EOQ. That's a very optimal situation because we assume all orders will be received instantaneous with no time. So basically this is not true in practice. So definitely it takes some time to receive your order. And so every time when we order, we have to wait for some days. And because that's apparently, order should be received slowly or gradually because of several different reasons. If we are working in a supermarket, so the raw materials will be from the outsider and suppliers, so deliver takes some time. So maybe every day we can receive part of our inventories, but we cannot immediately receive all. And if the sort of order is the productions from our own manufacturing lines, that's also the case. It's not possible to produce a huge amount of products in one day or without any times. So basically the manufacturing lines can produce for every day a certain amount of products and with a certain rate. So every day maybe we have a P or we have a 10 products produced, but the demand is 5, something like that. So that's basically a slowly process to aggregating our whole inventories. So, and that's the reason we're going to consider slightly more difficult situations in here. So previously we have the aggregating process very sharp in here. That basically takes no time. But in practical, it's not possible. So we definitely, the order receive time period takes some days in here. And so we aggregate the inventory level slowly. And one day we're going to aggregate all the required inventories. But one of the problems is that and during the time we receive our orders, we still need to supply our customers. So that means every day we receive some of the inventory, some of the orders, but at the same time, at the same day, we still need to sell out something to our customers. So that means we're gonna figure out so what is remained, what is sold out. So this is basically a ratio problem. But anyway, we need to understand. So we should have some time to wait in here until the total quantity of the order received and aggregate our total inventories. And one thing is the speed of receiving our orders should be faster than our customers' demand. Otherwise, we won't have any inventories. That's going to be a problem. Okay, so let's consider this case. This is a pretty simple and very straightforward example. For example, we're changing the story. So we are not working at a supermarket. So basically, we're working in a mill. So we're going to produce some of the rice. We are running our production line, and then we produce this product, and we produce product and sell the product to our customer. Okay, so if we're speaking of the production line, so we should have some production rate. So how many pallets of rice we can produce every day? For example, in here, this example, we give it a number 3 pallets per day we can produce. But during the days we are producing, we still need to supply, we still need to sell to our customers because they have demand. So for example, the daily demand is just 1 pallet. So that shouldn't be higher than this. If the D is higher than P, that's going to be our problem. So we need to increase in the P to make sure the P is higher than D. Otherwise, we don't have any inventories and we cannot satisfy our demand. So in most of the cases, we're assuming now we have a very okay production line. So the P is higher than D. Okay, so think about this is day 1. And we produce a 3 at day 1. But before day 1, we have nothing as inventories. So in day 1, we produce 3 pallets, but at the same time, we still need to sell out 1 pallet because this is the demand from the market. So after 1 day, we have basically 2 in stock and 1 pallet consumed. So this is actually pretty easy to understand. But in total, we produced 3. So part of our production are consumed by the market, and part of our production are stored temporarily as the inventories. So what is the ratio? Apparently, this is a 1/3. So 1/3 of our productions are consumed, and the other part are remained as the inventories. So how to find out the ratio? So that should be the daily demand divided by the daily production. So every day, if we consume 1 pallet, so in total we produce 3, so this is 1/3. So if every day we can consume 2 pallets, and every day we can produce 3, so the consumed are 2 divided by 3, and the remained is 1/3. Okay, so this is the ratio. So we can very easily to using the daily demand divided by daily production. Okay, so this is for 1 day. And second day, apparently, we can keep producing 3 pallets, and we can sell another 1 pallet for the second day. So in total, we have 2 pallets consumed by the market, and in total, we have 4 pallets produced in the first 2 days. They are the inventories in stock. But in total, the production is 6. So because this is a 2 days production. Every day, we produce 3, so 2 days, we produce 6 pallets, so in total. Okay, if going to the 3rd day, so apparently, so after the 3 days, we sold out 3 pallets, and so every day we sold out 1 pallet, so 3 days in total, we sold out 3 pallets. But in total, we have 3 pallets per day times 3 days, that's 9 pallets in total produced. That's our production. And so how many remain as inventories? So apparently 1, 2, 3, 4, 5, 6. So 6 remained in here as the inventories. So if we are standing here at day 3, so what is the ratio? We have 3 out of 9 consumed by the market. So the ratio is still 1 divided by 3, 1 over 3. So what is the ratio in stock? It's a 6 out of 9. So this is still 2 divided by 3. So same ratio as the first day. So in the first day, we have 1/3 consumed. In the last day, we still have 1/3 as the ratio consumed. So the other part are remained as the stock. Okay. So if, in this case, if we are running our production line for 3 days and then we stop for some days. So we don't know how many days, so we stop for some days and until all the inventories are sold out. And then we rerunning our production line again, starting the production line again to aggregating the inventories. And then after 3 days, we stop and we sell out all the inventories until we running out of inventories, and then we rerunning the production line again. So this is the process for this story. So every time when we're running our production line, so how many products we can produce? Basically, that's 9. So in this case, we consider the order quantity. And here is not order. So when we say order in this case, that's actually the production. So how many things we can produce. So order is from outside, and the production in this case is produced by our own production lines. That's basically the same thing. So we're going to aggregating the inventories. So if we order from outside, so the order is our inventory. If we produce our own products, so the production is our order. Basically, if we running a production line for 3 days, in total we produce 9 pallets. So that's our Q for this time. And production rate, so this is something we know, it's 3 pallets per day. So this is a daily production rate. And demand rate, so this is daily demand rate, so we also know, so 1 pallet per day. So running length, that's Q divided by P, that's 3 days. So running length, that means, so how many days we're gonna run in our production lines. If we know the production quantity, so order quantity for the whole, the production process is Q. And if we also know the daily production rate, so apparently we can find out how many days we run. Because in total, we produce 9. Every day we produce 3, so apparently we're running this for 3 days. So this is how we're gonna find out the running length. And so think about, so Q is the total quantity we produced in 3 days. And so how many remained after 3 days? So that's 1 divided by D over P. So D over P, that's actually the consumed ratio. So D is 1 and P is 3. So every day we consumed D divided by P. So this is the ratio we consumed. 1 minus this ratio is the ratio remained. So in total, Q is the total production. So in total, we have Q times the remained. That's actually equals to 6. That's the remained and quantity of inventories after our production, running our production line for 3 days. Okay, so this is from this pretty simple example. And let's take a look now about the theories. So this is the real numbers, and now let's think about the theories. And so we are running the production line from very beginning, and at the same time when we're running production line, we still need to sell out something. So we aggregating our inventories by a rate. So this is a rate is slightly lower than if we only have P, if we only produce without any consumption. But actually we have consumption. And so after several days, so in this case it's 3 days. So in here, we don't know. After several days, we're reaching here. So that means we aggregate all the required inventories. And then we stop our productions. And because we have inventories, now we have enough inventories and we stop. So, and then we start to only sell out our inventories. So every day we sell the same amount of inventories. So the inventory level are decreasing every day by the same rate until one day, so we're running out of our inventories. And then we're starting the production line again with the same production rate. And so the market demand rate is also the same. So we keep aggregating again. So this is the second cycle. And until one day we're reaching this point. And then we stop our production line and we sell out everything, sell out all the inventories by the same rate. So until one day we're reaching here. So now let's take a look, see how we're gonna find out those quantities. And for this, Q times 1 minus D divided by P, that's actually the total, the peak. So the total amount of production we can aggregate after several days running of our production line. So how to find out this? So this is actually from our very intuitive and derivation of the equation, because every day we consume 1/3. So 1/3 is from D divided by P. So 1 minus D divided by P, that's every day what remained. And in total, in 3 days, we produced Q, so times the ratio of the remainder ratio. So that's actually the total amount of inventories we can aggregate after the first running of production lines. Okay, so in this case, the daily production rate is P, and we know this. And daily demand is D, we also know this. And also we assume number of days per year, so that's total number of days per year we are working is Y. That's also something yearly we know. And so the annual demand, apparently, is D times Y. If we only consider Y days, for example, 360, or maybe sometimes we consider 5 days a week and 52 weeks a year, so that's another number of days in a year. So this is annual demand. And so consume the ratio. So that's always be D divided by P, because every day we can produce P, but every day the market requires D. So this is a consumed ratio. And remain ratio, apparently 1 minus the consumed ratio, and this is something remained. So production lot size, so that means, and after every cycle of the production running, so total produced quantity in every production run, that's Q. Q means, so this is actually the time we are running our production. So how many products we can produce in total, that's basically Q. So Q is the total produced products. So the remaining production is Q, the total produced one, times the remaining ratio. So that's the remaining inventory levels at this point. Okay. So, and apparently if this point is this, so basically the average inventory level is basically the half. So we can, if we hope to find out this, so an easy way is we're gonna put in this small triangles and to here, and also we can put in this small blue triangles and to this part. So this is basically how we're going to find out the average level of the inventories. Okay, and production run length. So if we know Q, that's the total production, and we can produce a total quantity of products we can produce during several days. So, and every day we can produce P. So how many days are we running? So Q divided by P, that's apparently. Total cycle length. So what is a total cycle length? So this is something I think is slightly interesting. And total length is in here, cycle length. So that means from very beginning we have nothing in the inventory to, and we run in a production line, we aggregate to this level, and we stop production line, and we're trying to sell out everything until one day again, our production, our inventories is 0 again. So the total is, so what is the total days? Is it Q divided by D? So how to find out that? So that's basically from 2 things, and one is production run. So we know production run is a Q divided by P, apparently. So this is a Q divided by P. And so what about this part? So this part actually, we don't running any productions. So if also consider this part. We don't run any production, so we only sell out. And we know the sellout rate is D. So every day, the market requires D. And what is the total quantity at this point? Is Q with times the remained ratio. So this is the total quantity, and every day we sell D. So we're gonna using a total quantity divided by everyday sales, so we can find out how many days we need. So finally, we find out this is a Q divided by D. So this is a total cycle length from inventory of 0 to another inventory of 0. Okay, so now we trying to find out the, so where it is? Yeah, so we're trying to find out average inventory levels. So this is the average inventory level. And if we know the average inventory level, so apparently we can know the holding cost. Because that's apparently, because the holding cost is the average inventory level times the unit holding cost. So no, this is the new average inventory level. So this is the holding cost. If we know the unit holding cost, so we times together. So that's the total holding cost. So what about ordering cost? That always be the unit ordering cost for every order. So this is the unit ordering cost times. So how many orders we need to make. So this is the ordering cost. So now let's try to find out again what is the optimal order quantity. So apparently we need to make this holding cost and equals to the ordering cost and find out what is the optimal one. So we make this part equals to this part and trying to, manipulating things and figure out this is the optimal one. And another way is we know this is the total cost. So this is the holding cost. So average inventory level times the unit holding cost plus the ordering cost. So this is the total cost. And we try to find out the first derivative of the total cost to Q and make it to 0. We can find out the same result, same expression as this. So this is also two-way. But for this time, so if you find out the first derivative, it's slightly more difficult. But a slightly easier way is we're gonna making holding cost equals to the ordering cost. That's slightly easier to find out what is the optimal quantity. Okay, so if we know the optimal quantity, so that's at this intersection point, and this is how we're gonna find out optimal point. So we can make the two part the same. And if we find out the optimal quantity, we can substitute into ordering cost and holding cost and find out what is the total cost in here. Okay, so this is a sum of the summaries for the non-instantaneous receipt model and a lot of equations. We're gonna try to do some calculations. Okay, so now you are trying to processing your rice. It's not just ordering and sell out. You are trying to processing. So you have your production line and you know that the setup cost for your production line is 150. So setup cost, that's basically could be equal or interchangeable to our ordering cost. Ordering cost is for ordering from our outside suppliers. And setup cost is for our own production lines. So that's basically the same. Every time we set up and we're starting up our production line, we need some cost. Every time we're ordering from outside, we also need to pay for the delivery or something. That's basically interchangeable concept. And the annual holding cost is basically based on how many bags we have. The company operates how many days? 311 days a year. And the yearly demand, so this is the total demand for a whole year. The big D is this. We estimate it. And factory capacity is 150 bags per day. So this is actually our everyday production. Okay, so we know several things how to find out the optimal one. And first of all, we need to know how many quantities we need as a demand for every day. So this is the total demand divided by the days. So this is every day we need to supply the market, supply the customer. And production rate, we know, so this is 150 per day. So apparently this, okay, we can aggregate some inventories because this is much higher than the P is much higher than the D. So we can immediately using this equation. 2 is constant. D is the annual demand, 10,000. And CO, that's the setup cost or interchangeable to ordering cost. And CH, that's the holding cost. And then we have a P divided by P minus D. So P is our production rate, daily production rate, and also D in here that's the daily demand from the market. And then we can find out this is the how many bags and we should produce every time when we run in the production line. Yeah, please.
Should these formulas be given in the exam?
Answer you later on, not now. Yeah, I assume this is always be the question.
There are many ways to get the answer, right?
Sorry?
There are many ways to get the answer, right?
Many ways. For example?
No, in the sense that there is no other formula to this. There's no replacement. Is this the only formula we can use?
Yeah, that's the question I'm asking you. Is there any other formulas we can find out this?
I'm asking you, I don't know.
So actually, because if you basically if you listen to me carefully before, so and for this formula, because we derived from what? Holding cost equals to the ordering cost. So that's the theories. So actually, you don't need to remember exactly what the formula is, but if you know the theories and we know the everyday production, everyday demand. So apparently, what is the remain ratio is 1 minus D divided by P. You know that, and actually, you know how to find out the holding cost, and you know how to find out the ordering cost. So make them the same. So that's pretty easy to find out what is the optimal quantity. So you might not need to write down this formula, but you might need to, you have to, starting from the theories. If you don't remember this, you could say, okay, I know I want to find out the optimal one, but how to find out, and the easy way is to make them the same. So you can find out, okay, write down, okay, so this is the ordering cost, and this is the carrying cost, and we make them the same and find out this. That's also basically the same way, but you may have to write down the same things, but actually the logic is the same. Yeah. And so if you find out the optimal quantity for every production running, and so you can easily find out so what is total cost, because this is the holding cost and this is the ordering cost, and also how long it takes to produce and this amount of optimal quantity. So because we know every day we produce roughly 150. So we use, this is the Q and divided by P. So this is how many days we need to run. So basically we need to run roughly 15.1 days and for every production cycle. And how many production runs? So, because we know every day the total demand from the market for a year is 10,000. And the Q, we find out the Q. The Q is every production running, so we have to produce 2257. So how many rounds? So that's basically using the total demand divided by every time and how many products we can produce. Yes, please?
To work out the optimum,
Mm-hmm.
do we use per day or per month? Like, for example, if you produce like certain amount per month,
Mm-hmm.
we use per month instead of per.
Yes, I think that's a correct one. So, but for most of the cases, for this example, so we only consider day and years. Because the reason is that, so most of the cases in the production, in the manufacturing process, we don't consider like the month, but we only consider how many working days. Because every month have different days. So we consider, so okay, we working 6 days a week, for example, and we keep running this. So this is we're based on days and a year. So that's usually the case. So for basically, I can see for this type of inventory question, so you won't see any like a month. So you can only see, okay, we are working how many days a year, and that's basically the only thing you should know. So how many days? That's fine. Yeah, we don't consider month. Okay. So Yeah, we know the total demand and we know Q, that's the quantity for every production running. So we know we need to run 3.43 runs for every year. And so what is the maximal inventory level? So apparently we know Q, and we know after every running, so we have a certain ratio of the inventories remained. So this is the ratio. We can find out this is the maximal inventory levels after every running. Okay, so that's the second case. And apparently we could have another case. So this is the very beginning. So we assume we order from our supplier and then immediately having a queue, so without any delays. And every time when we have 0 inventories, we can immediately order and then we can immediately aggregating. But the problem is that sometimes maybe and we are short of inventories because of several reasons. Maybe supplier's problem or production breakdown, or maybe we forget. So sometimes, and this is the case in practical, and when we have a inventory 0, we cannot immediately aggregate our inventories. So we have some time, for some days, we have some shortages. So we know we need to order and we need to aggregate inventory immediately, but for some reason, we cannot just get them immediately on our hands. So that's going to be a problem. So, and for this case, for example, if we have inventory 0, we still have a demand from our customers. We have to give a promise. Okay, yeah, fine. Okay, I'll deliver to you some days later, but I'll definitely do that. Otherwise, I have to pay some penalties. So I have to aggregating for all the demands from the markets. And once we have some inventory levels, I deliver. So this is called back orders. So I deliver for all the basically shortages to the customers immediately. And then after the S level of the shortages, and then I can aggregate my inventories again. So in this case, we are not considering the time for delivery. So we think about only, okay, so we can receive our order immediately, but for some reason, we have some shortages in here. So this is an optimal solution, but we don't consider them together because for simplicity. Otherwise, it would be very complicated. Okay, let's take a look on this. So, and each time when we receive the products, Q, so the first of all, we need to refill our inventories. So we have to refill this because at this time point, and we don't have inventories, but we still have some demand from the market, from the customers. So we have to write it down. Okay, so this is a negative, so we don't have any. So we're going to deliver you later on. So once one day we have all the inventories, we have refill those requirements, and we deliver all the requirements from the customers we promised before. So until we don't have any basically shortages from here. So and then we aggregate our inventories immediately. So that means if we allow S level of shortages, and every time we order Q, but all we can aggregate is just a Q minus S, because at the very beginning we have to refill the shortages from the market as the first thing. And in this case, we consider T1 as the time that we hold some inventories, and T2 is the time of the shortage. In total, we have time of T, so apparently. So because we considered this before, if we only consider T1, we have some inventories at the very beginning. And at the very beginning, the inventory, the highest level is just Q minus S at this point. So if we only consider T1, so what is the average inventory level? If we only consider T1, because we've done this before, so this Q minus S divided by 2, if we only consider T1 in here. But if we also consider T2, so we don't consider negative. So in T2, basically we have 0. So this is all 0 for T2. So if we want to calculate for the whole average level of inventories, so we're going to find out this is the total amount, and for T1, and this is for T2. Apparently we have 0. And the total time is T1 plus T2. That's T So basically, we find out that if we consider T1 and T2 are all zeros, so the total average inventory level is Q minus S divided by 2 times the ratio of T1 to the total T. So this is the average level. Okay, let's take a look. So if we only consider and T1, so this is basically the average level in here, if we only consider T1, but if we consider T as a whole time period, so that apparently we have slightly lower average levels in here. Okay, so we have to figure out several relationships between this, because this is, I think, easy to understand. At the very beginning, we have no inventory, and we immediately aggregating Q minus S, and we keep selling out and keep selling until one day I have 0, and then we have shortages and by the same rate until one day to here. Okay, so now we have several small triangles here. So this is the first triangle. So, and we know this is a Q minus S, and so this is T1. And this is the first one. And the second one is a small triangle. And let's see, so it's actually in here. So this green one, small here. So this is T2 and this is S. And okay, so this is the second triangle. Actually, the small green one is pretty much similar to the previous one. And the last one is a blue one, it's a bigger one. So, and this is actually Q. And so this is actually T. So if we looking at this again, looking at the three small triangles, and this is Q, this is T, and this is S, this is T, and this is Q minus S, this is T1. So they are all very similar. So that means the ratio of the certain edges are the same, because they are actually the same triangles with a different size. So the angles are the same of this one and this one and this one. They are pretty much the same. So because of the similarities of triangles, we can have the certain ratios of this. If a Q divided by T, that should be equals to Q minus S divided by T1, because this is the similar triangles, and equals to S divided by T2. So this is the relationship we should have. So if we have this, we can pretty easy to find out. From this, we can interchange Q and T1. So we should have T1 divided by T, that's basically equals to Q minus S divided by Q. So this is the same ratio. And also, if we have a Q divided by T and S divided by and T2, we can have this ratios. So this is pretty important for the future work. So let's think about, if we only consider T1, the average level, inventory level is this, but we have to consider the whole T. So this is actually the total average inventory level, and Q minus S divided by 2, but we have a T1 divided by T. So, but we derive the T1 divided by T, that's basically equals to this. So we can substitute in Q minus 1 divided by Q into this, and we have, this is the total, and total average inventory levels. And if the holding cost or carrying cost is CH, so this is the average inventory level, and we times the cost, that's basically the total holding cost. And apparently for the shortage levels, so the shortage, the maximum level is S. So the average one is S divided by 2, because it's a small triangle, that's pretty easy, and times the time ratios in here, and T2 divided by T, because we know this is equals to S over Q. So we're substituting, we got, this is the average shortage inventories. So if we know the shortage cost is CS, so we times the average shortage inventories, quantity, so that's the shortage cost. And also the ordering cost is the same. So how many times do we need to order? So D divided by Q, so this is the ordering cost. Okay, so if we know the holding cost, shortage cost, ordering cost, so we add them together, so that's the total cost for this case. If we allow some shortages, even we don't allow any delivery time, so the total cost are a little bit more complicated. For this case, how to find out the optimal quantity of order Q. So actually there's only one way, so this is the total cost, is so we're gonna have to try to find out the first derivative to Q and first derivative to S, and to find out the first derivative and make them to 0 and try to find out what is the optimal S and Q. So if you are interested, you can try to see how it works. And so to find out the first derivative to S, so we can find out basically the optimal relation between S and Q. So, and to find out the first derivative to Q, so to make it 0, you can basically find out the relation, another relation of Q and S, and you substituting together, and you can find out this is the Q square, and you are finally manipulating everything, you finally find out this is the optimal, and for the Q. And if we know the optimal quantity for the Q, because we know the S, so this is actually the optimal quantity of S. So that means that you cannot give whatever shortages you like or whatever shortages your customer like. So this is the optimal quantity of shortage if you allow some shortages. Okay, so this sounds like not easy to derive, but actually this is pretty much just simple calculus. You could try to find out later on if you are interested, but you're not required to prove this in your exams. So apparently, so this is some summaries for the last case. If we allow some shortages, apparently the scenario is much more complicated than before. So, this is some of the total summaries for 3 cases: EOQ, EOQ with non-instantaneous receipt, and EOQ with some shortages. And so apparently for all the cases, the annual demand is the same, daily demand is the same, the annual production is the same. For EOQ, actually, we don't have any daily productions because we don't consider that. So this is one of the assumptions for EOQ. But for this, because this is we consider any production rate and also some consume rate. So we consider P and D. For shortages, apparently again, because we don't take any times to receive any orders, so we don't consider any production rate. So days of a year, so apparently the same. Carrying cost, ordering cost, shortage cost, that's the same. Also shortage cost is only for this. And apparently we can have derived for different optimal quantity equations in here. And total carrying cost, that's pretty much the similar things. So that's based on the carrying unit cost times the average inventory level. So, and ordering cost always be the same, because if you find out the optimal quantity, so you find out how many orders you have to make, so times the unit ordering cost, that's your total ordering cost. Okay, a lot of equations in here. And that's actually most of the theories we need to introduce for inventory system. And this is a pretty simple summaries. Equations. So, and actually Wolfgang suggests we don't need to give the equations in a final exam. This is his suggestion. So, but I guess maybe it's not the best way. So some of the equations will be given, especially for EOQ and EOQ non-instantaneous, because for most of the cases and for the shortages, that's much more complicated. So usually we don't test that in the exam. Usually, I said. So for the optimal quantities for EOQ and EOQ with the non-instantaneous, so those equations will be given, but you still need to understand what is CO, CC, what is D, what is whatever symbols. If you don't know what is that, that's going to be your problem. And one thing is, nobody is going to tell you which model you're going to use. So you have to figure out by yourself. So basically, there's only one criteria. It's very simple. If you know the daily production rate, P, that means that you're going to using this with a non-instantaneous receipt. That's because we have to consider the daily productions. That means daily production takes some time. We cannot assume we have all the inventories immediately. So if we don't know the daily production, so that's probably we're going to use the EOQ. That's a very simple case. Okay, so that's all the theories. And one thing is, in this week's lab, we're going to do 2 labs. And lab session 9 and 10, we're going to do them together. The reason is that in the last 2 labs, so basically we don't have any real labs. So we don't need any Excel and skills. We're just trying to solve these calculations. And so we're going to try to summarize all the equations in the lab session and to figure out for several different questions how to solve this inventory questions if we see different stories, different business cases. So we're going to try to make the equations there, make the formulas there, and figure out, so for this certain questions, which formulas we're going to using, and for that certain questions, which formula we're going to using. So we can basically solve all the questions very quickly if we figure out all the questions in Excel. So we're going to do them together in this week. So that means you could do the assignments for week 9 and 10 in this week together. Actually, they are all open. They've been opened now. So if you could finish by now. And that also means in next week, we don't have any lab session. And also week 11, we don't have any lab sessions because we've done all the lab sessions in this week. Okay? So, but we still have lectures in the next week. So some exercises for inventory system. Okay? So thank you guys.